Okay, so we left off in the last video talking about this heat of atomization, which was the energy taking elements in their natural state and separating them into individual gaseous atoms. And we did a question where we looked at some reactants. It was sulfur trioxide, and I asked how much energy does it take to break everything apart into individual gaseous atoms, and we added the heat of formation for sulfur trioxide, and then the heat of atomization for all the component elements. Okay, so essentially we took some compound and then we broke it all apart, or we overcome the bond energy. So here you can see in the diagram we've been getting to this point here where we're working out the energy in all the bonds in a compound, where the bond energy, let's call it, or the energy in all the bonds, is equal to the heat of formation, or the negative heat of formation, plus the heat of atomization for all the elements in there. So we can work out how much energy is in the bonds. Okay, so here I've got, I don't know what I'm trying to represent here. Let's call it, oh, you know what? It could be hydrogen and oxygen, H2 and O2. Okay. Oh, let's call it hydrogen peroxide. Let's call this H2O2, okay? So to go from H2O2 to H2 plus O2, that equals the negative, or going in the other direction, of the heat of formation, okay? So the heat of formation of H2O2 is the energy between those H2 and O2 and H2O2. So many H's and O's, okay? And then we're going up again and we're doing a heat of atomization where we're taking H2 and O2 and we're splitting them apart, okay? So therefore, the energy required to go from here, where we've got 2 hydrogen atoms and 2 oxygen atoms, down to here, H2O2, is called the bond energy. It's the energy in our 1, 2, 3 chemical bonds in there, our covalent bonds. So the energy in those 3 covalent bonds is equal to our negative heat of formation plus the sum of the heat of atomizations, okay? So it's another pathway that we can use and follow Hess's law, okay, to work out what the bond energy is. All right, so the bond energies equal the negative of the heat of formation, because we're going in the opposite direction to the heat of formation, and then just the heat of atomizations, or the sum of them, okay? So let's do an example here. Determine the amount of energy in one nitrogen-hydrogen bond of ammonia given. Notice what the question here is asking. Here is ammonia. I haven't drawn it in 3D, I'm sorry. But we've got 3 bonds, okay? And we've got 3 identical bonds. So if we work out the total energy in those bonds, each is going to be 3 times the nitrogen-hydrogen bond, okay? So we're asking for energy of one of those bonds, so we're going to work out the total energy given the heat of atomization and heat of formation, and we're going to get the total energy and divide it by 3 to get 1 nitrogen-hydrogen bond, okay? So we're starting here at ammonia, and we're taking it up to the heat of formation. So the heat of formation for that value will be going to half of N2 plus 3 halves of H2, okay? Because nitrogen exists as N2 and hydrogen exists as H2, okay? And then we're taking it up somewhere where that's just equal to the negative heat of formation of NH3, okay? And then we're taking it up to the atomization level where we're going to have a nitrogen atom gas and 3 hydrogen gaseous atoms. So we're going to need 1 times the heat of atomization of nitrogen plus 3 times the heat of atomization of hydrogen. Okay, so E total equals the negative heat of formation of ammonia, and the heat of formation of ammonia is negative 46, so the negative of the negative is plus 46. And then we're going to add on 1 times the heat of atomization of nitrogen, which is 473 kilojoules per mole, and 3 times hydrogen, which is 218 kilojoules per mole. So my total energy, put it in my calculator, 46 plus 473 plus 3 times 218, and I get 1173 kilojoules per mole. And that's the total energy in all those 3 covalent bonds. So just the nitrogen-hydrogen equals 1173 on 3 kilojoules per mole, which equals, got it in my calculator still, so 391 kilojoules per mole for the nitrogen-hydrogen reaction. So we've got that one bond energy. So we did it by calculating the total bond energy and dividing by 3. And we got the total bond energy by working out what's the negative heat of formation, or the energy to go from here to here, and then the energy to go from here to here using the sum of the heat of formations. Okay, let's just do another variation. Determine the amount of energy in one carbon-hydrogen bond of CH4. So methane, that one's called. Okay, so one of those so the energy for CH is going to equal E total divided by 4. Okay, orange is horrible. Why am I writing in that? Okay, so we're starting down here at CH4 gas or methane gas, and we're going up to a point which is the negative heat of formation of methane. So carbon in its natural state is just carbon solid. And we've got 4 hydrogens, so that's 2 H2 gas. Okay. Alright, so hydrogen's found as H2. So that's the heat of formation level. And then we're going up to the heat of atomization. So we've got 1 carbon gas, and we've got 4 hydrogen gas, separated atoms. So this is going to be the heat of formation, the heat of atomization of carbon, just 1 times that, plus 4 times the heat of atomization of H. Should I change my color? So the heat of formation is given as negative 75 kilojoules per mole, so the negative heat of formation is plus 75 kilojoules per mole. And the heat of atomizations of carbon is 717, and 4 times hydrogen, which is 218 kilojoules per mole. So E total equals the 75 for the negative heat of formation, plus 717 plus 4 times 218 kilojoules per mole. So 1664 kilojoules per mole. So methane as total in all those 4 bonds has 1664 kilojoules per mole. So for each bond, it's that divided by 4. So carbon-hydrogen energy equals 1664 on 4 kilojoules per mole, which equals 416. That's terrible writing. Let's erase that. 416 kilojoules per mole. Alright, there's some worked examples from the textbook. Or should I keep going? Alright, nah, oh yeah, let's do this one. Okay. So let's keep going. Sorry about that confusion. Okay, so reactivity, stability, and bond energy. So we talked about reactivity and stability, talking about energies early in the chapter, but we can relate bond energy as well. They're just expressions of the same concept. So we're linking bond energy in there. The greater energy in a bond, the less reactive that molecule is, and the more stable it is. okay? But also, I'll talk about it on the next one. Okay, so let's look at two examples. For example, oxygen is a very stable molecule, while ozone is more reactive. Okay, so oxygen has just one bond, or one double bond in it, and there's 498 kilojoules per mole in there. Larger bond energy, it's higher stability and less reactive. Okay, so in ozone, there's two oxygen bonds here, and I know how we draw it during Lewis structures, but it's like they have 1.5 bonds each. They're 302 kilojoules per mole each. So you can see there's less energy in those bonds. So smaller bond energy, lower stability, higher reactivity. So ozone is more reactive than oxygen because it has a lower bond energy and therefore a lower stability, more reactivity. Okay, now let's compare water with hydrogen peroxide because they're just hydrogen and oxygen, okay? But the trouble is we've got different bonds here. So in water, we've got two OH bonds, and so they have 463 kilojoules per mole each. But you can see that we've got, in hydrogen peroxide, we've still got the two OH bonds with 463 kilojoules per mole in, but we've got the OO bond, and look at that. 146 kilojoules per mole, so a lot less. So that oxygen-oxygen bond in hydrogen peroxide is causing the molecule to be more reactive. Okay, so a molecule is only as stable as its most unstable bond. Okay, so water is much more stable than hydrogen peroxide because of that 146 bond, okay? So when energy comes in, it's more likely to cut through there and cause two peroxyl radicals. Pushing it there, I know. Okay, so a molecule is only as strong as its weakest bond, okay? That's what I'm trying to show here. So water under standard temperature and pressure is very unreactive and very stable. We know that from everyday experience. Okay, hydrogen peroxide, you can buy a solution of it, but that solution is usually stored in a black coloured bottle and with its lid on. And what happens is that hydrogen peroxide over time, it decomposes and it is spontaneous. Okay, spontaneous decomposition of hydrogen peroxide. It forms water and oxygen over time. If you leave a bottle with its lid off, over a matter of weeks, it's all going to decompose. It's a slow reaction. You can fasten it up though, and we do that, and sometimes called elephant's toothpaste, where we put a catalyst to cause faster decomposition, and that's when you put like detergent to capture the oxygen bubbles, and you get all those fun bubbles going everywhere. Okay, so hydrogen peroxide is much more reactive or much more unstable because of that weaker OO bond. Okay, so there's a table from the textbook with bond energies in there, which we're going to use in the next video and in problems.